Welcome and thank you for downloading the SteerDuff podcast.
Welcome. No? Yes, please, thank you. Welcome at the second part of the lecture series of Introduction to Aerospace Engineering. My name is Hester Bijl. I'm full professor aerodynamics, and I will teach you the part focused on aerodynamics the coming 2.5 weeks. The first lecture, so the main book is Introduction to Flight, so still this one. And we hop a bit through it because the standard atmosphere in chapter 3 has been treated already. But I would like to start with the basic quantities in chapter 2 today and then skip to chapter 4. Lando Timmer is teaching the Dutch class, so my colleague. Okay, so Anderson, chapter 2, and chapter 4.1 to 4.3 today. And quite important people for this part are Leonhard Euler and Daniel Bernoulli. Well, aerodynamics, as you understood probably already, you've been working with concepts of lift and drag already, is crucial. Yes, question? The lights down, yes, I can. Ooh, yeah. No, I cannot. Yeah? Better? Okay. So fundamentals of aerodynamics. Well, aerodynamics is crucial to flight of aircraft, of course. If we didn't have air flowing over the wings of the aircraft, we couldn't actually fly. So what we will do in the coming 7 lectures is first teach you the basic principles of flow, the physical principles you need to know before you can really go and play around with designs of wings and aircraft. Then in the second part, we will go in detail on concepts that are relevant for the aircraft. So lift, drag, viscous flows, how they affect the performance of the aircraft. So 2 parts. The main bodies are the chapter 4 and 5 of Anderson. Chapter 4 is the fundamental quantities and basic concepts. Chapter 5 is focusing on wings, airfoils, and shapes relevant for aircraft. And today we'll start with a quick introduction from chapter 2 and 4.1 to 4.3, and then we'll continue along. Important people are Leonhard Euler and Daniel Bernoulli, who have worked on concepts that are very relevant for fluid dynamics and aerodynamics. Yes, better. Okay, so the first hour today, fundamental quantities, density, pressure, temperature, velocity, crucial if we talk about fluid flows. And they may sound sort of trivial to you, and after this we will only talk about the dimensions and the concepts, but I would like to define them so we know what we're talking about. And it's sort of good to have really the basic fundamental concept. And then the relation between these two, the equation of state, coming from chapter 2, you've played around with it already in the with the standard atmosphere, but I'd like to make you aware of this relation between the basic quantities. Then in the hour after, so in the second hour of the lecture, we will move to, bless you, we will move to the relations between velocities, so not only the basic quantities, pressure, density, and temperature, velocities and pressure. Okay, so pressure, density, temperature, velocity, equation of state. No, this is not working. Yes. Okay. So what is pressure? Well, pressure you feel when you push on something. So pressure is force on something, force on a surface. So quite often people get confused about the dimensions of pressures. And if you think about what pressure is, so pressure you can push on your hand, or you can feel air pushing on your hand. If you put it outside of a car window when somebody's driving, you can feel a certain force. Well, pressure is force on a surface. So it is the normal force. So it is in a direction normal to the surface, and it is force per unit area. So how do you then define pressure in a point? Because we work with pressures in points in this room or in certain flows. Well, you define this by taking an infinitesimally small, so a very small surface area. Think about the force on that and then take the surface area to 0. Then you have a definition of pressure in a point. So suppose we have here a blob of gas or flow, and we have a surface at this blob called B, and we have a certain small, so this is already a small surface, a certain small force on it, in the normal direction. So this is an element surface, and we have here this small surface, and we have a small force, dF, on one side, normal direction. And the pressure is defined as force per area, so dF over this small area dA, in the limit when this dA goes to 0, so when the surface goes to 0. So then we have it in a point. Important to remember is the dimensions of pressure. So dimensions of pressure is the dimensions of force divided by the dimensions of area, right? And we work with SI units, so that's Newton over meter squared. So this is important to remember, Newton over meter squared for pressure. Well, we can do the same with density. Density, we would like to talk about density in points in the flow, any point. Well, density says something about how many kilograms fit in a cubic meter. So, sort of how much weighs a cubic meter, a certain volume of gas. Well, that's sort of a volume. So how do we go from this volume to the point? We do the same trick again. So in this case, we have a very small volume, dV, here at this point B. And then we say, okay, density is the substance, the density of a substance is mass per volume, so kilograms per meters to the third. So we start with this very small volume, and we know how much it weighs, and then we take the volume to 0. So density is then mass, so the small mass of this volume we write down as dm over the small volume, dv, when we take the volume to 0. And then, of course, what is the unit? The unit of density is the unit of mass per volume, so the kilograms per meters to the third. So again, then we have it in a point. So that was pressure, density, now temperature. Temperature is defined differently. Temperature of a point, the temperature of a point in a gas is related to the kinetic energy of the gas. And what is kinetic energy? Well, each gas or liquid consists of molecules. And these molecules move. They have a certain kinetic energy, they sort of vibrate. And this vibration, this kinetic energy, is related to the temperature. And this is one of the fundamental relations of temperature, you see it here up T, and kinetic energy. And how are they related? They're related linearly with a certain 3/2 and a certain Boltzmann constant, which has a dimension, Joule over Kelvin. So this temperature, high sort of kinetic energy in the gas, so the molecules are sort of vibrating quickly. What dimension of temperature do we work with? Well, of course, if you're Dutch, you're very used to the Celsius, 15 degrees Celsius, 20 degrees Celsius. But actually, we prefer to work with Kelvin. So we work with the dimension of temperature, Kelvin. The relation between Kelvin and degrees Celsius is not so hard. They only have a different point of 0. So Kelvin, you can work from the one to the other. Like with this, Kelvin is 273, if you want to be very accurate, 0.15 plus Celsius. So 15 degrees Celsius is 288 Kelvin. Now, what is important is the relation between these three. We have pressures, densities and temperature. And they are related. So once you know two of them, you can find the third. And how are they related? That is with the equation of state, it's called. And the equation of state is the following. There are different forms. Some people at high school have had a molecular form, well, where they think about sort of moles of gas, the equation of state. We think the equation of state as sort of points in our gas, and then the only difference is that we have a slightly different gas constant in this equation of state. So the relation is the same, but we have a different form of the constant. But please, this one you really should remember, crucial. An aerodynamicist and an aerospace engineer should be able to wake up in the middle of the night and reproduce the equation of state. Crucially important. That is the relation between pressure, density, and temperature. Now, how are they related? P is rho RT, and this R is the gas constant. And in R form, this R, and you should also remember, I made this sort of this gray, well, this brownish area. That means that you really should remember it also for the exam. P is rho RT, and R has a specific value, 287.05 if you want to be very specific, but we typically work with 287 joule per kilogram Kelvin. And if you don't remember, for example, the dimensions of this, you can think joules, kilograms, kelvins in relation with the kelvins here, the kilograms per meters to the third, and the newtons per meter squared. So you can find actually dimensions of these, if you forget dimensions of one of these, you can, by comparing the dimensions on one side of the equal sign and the other, you can actually find out dimensions. Yeah, so P is rho RT, and R is 287 joule per kilogram Kelvin. Now this is the equation of state this is sort of the easy equation of state. The true equation of state is more difficult, and it has more terms. So not only P is rho RT, but we have some extra terms. Where do these extra terms come from, and when are they relevant? They're not relevant for typical aircraft applications. They might be relevant for very dense gases in engines, for example, but in this course we will assume that we can always use the easy form of equation of state. And what is the difference? Well, the previous equation of state is the equation of state for a perfect gas. And what is the definition of the perfect gas? The definition of a perfect gas, a gas again, molecules. The perfect gas, these molecules don't notice each other. So the intermolecular forces between the molecules in the gas are negligible. And that is true for sort of any normal gas at here, sea level, normal conditions. When you really compress a gas very much and the molecules come very, very, very close, you have a non-perfect gas anymore. And then you can get additional terms. You get additional terms in your perfect gas equation, and that is these terms with constants A and B, and you get a more complex relationship. You get the P over T in here and the P over T to the third. And this is called the Berthelot equation. And well, the main difference is that if you look at it for the non-perfect gas, you see that if the P decreases, you get here smaller P's. Then normally you get here a larger T. However, you get here also other T terms. So the temperature then increases. So, but this is related, so only when the distance between the molecules is really small, you need to use this one. So you can forget about it, you should be aware of it, because you might need it once every while, but only in rocket engines or so. Yes? A and B are, I didn't write them down. A and B are constants, like the R, the gas constant, but they have different forms. Okay, so now that we have the equation of state and we have P, rho, R, and T, we can play with these things. And we can start making very simple examples. So first example is compute the temperature on a point on a wing. It's example 2.1 from Anderson from the book. On a point of a Boeing 747 where pressure and density are given. Well, what relationship do we have between pressure, density, and temperature? Rho RT. P is rho RT. Indeed, equation of state. Yes. So, equation of state. We're looking for the temperature, so we have P is rho RT, so T is P over rho R. Well, simple, pressure is given 1.1 times 10 to the power 5. Rho is given 1.2. What do we do with R? 287, yes. Perfect. And we find that it's 319 Kelvin. So simple relationships we can play with. Of course, it will be more difficult later. Then there are certain conditions that you need to remember. You cannot remember, of course, all conditions at all heights. Jacco Hoekstra introduced you to the standard atmosphere. You should remember the values of the rho, P, and T at standard sea level conditions. And what are these? Well, P is 1.01 10 to the power 5, or if you want to be accurate, you take into account the 325. So 1 atmosphere actually. That's the pressure at standard sea level conditions. The density is 1.225 kilograms per meters to the third. And the temperature at standard sea level conditions is 15 degrees Celsius, which is equal to 288 Kelvin. So please also remember these. It's important for, of course, an aerospace engineer. Also, the exam, we assume that you know these conditions. All the others you can, of course, derive using the standard atmospheric relations. Okay, then we can also do something like computing the total mass of air in a room, something like this, of 30 meters by 50 meters by 3 meters. We will use the computational approach of this later in the second lecture. So how do you go about this? Suppose I ask you this: what is the mass of air in this room? Yes. Density, very good start. Density is mass per volume. Yes. So mass is density times volume. So what is the density? Standard conditions, 1.225, thanks. So standard rho at standard sea level. The volume's given there, 30 times 15 times 3. The volume is actually 1,350 meters squared. Sorry, meters to the third, thank you. And then you find that the total mass of air in this room, 1,654 kilograms. So quite a bit. And indeed, if you have no idea how to do this, you can think, okay, density was kilograms per meters to the third. So through the units, you can come to this solution. Okay. Now, density tells you something about the mass of a cubic meter. So how much it weighs, or the mass of this lecture hall. But sometimes it's the other way around. You're interested in how much space does a kilogram of gas occupy. And that is the specific volume. We're struggling a bit with the notations. Oops, sorry, we're struggling a bit with the notation. So the curly V is used in Anderson. And I'll try to stick to that. So the definition is very simple, 1 over rho. So then the dimensions of the specific volume, specific volume is 1 over rho, so that is 1 over kilograms meters to the third. So it's meters to the third per kilogram. So it's quite simple. Why would you even be bothered? Well, sometimes it is easier to think about how much a kilogram, how much space it occupies. And then you get, of course, slightly different form of the equation of state. P is rho RT. So we had here rho. So if you have the specific volume, 1 over rho, you have P divided by rho is RT, or PV is RT. We will get some other V's for velocities later. So curly, small curly V is specific volume. Okay, and then you can do simple things as this. Compute the density and specific volume of air in a wind tunnel at a certain pressure condition and a certain temperature. So how would you go about this? Choose the right units first. So let's see. Compute the density. So density, we're looking for density. Kilograms meters to the third. The right units. So we have P in atmosphere and temperature in degrees Celsius. So how do we go from atmosphere to newtons per meter squared? 101.325. Exactly. So P. So this you should always remember. So 0.3 atmosphere is actually the same as 0.303 10 to the power 5 newtons per meter squared. Then we have a temperature, but it's in Celsius and we need it in Kelvin. Simple again, minus 100 degrees Celsius is equal to minus 100 plus 273 is 173 Kelvin. Now how do we compute the density? Density? Anyone? Sorry? 1 divided by the specific volume. Sure, so how do we compute the specific volume? Rho V is equal to RT. Sorry, PV is equal to RT, right? Or P is equal to rho RT. Okay, let's take the PV form. So V is equal to RT divided by P is equal to R is 287. Temperature we just computed 173 divided by the pressure 0.303 10 to the power 5. And then we find the specific volume 1.6 meters to the third kilograms. So PV is equal to RT. And then indeed rho is 1 over. And we find 0.61 kilograms per meters to the third. So simple. You could of course also compute first the density and then the specific volume. Okay. So these were all point properties and scalar quantities. So these quantities, pressure, density, temperature, are scalar values. Of course, in the flow, we also have velocities. And velocity don't only have an absolute value, a speed, but also a direction. So we have here a vector, a velocity vector. And then an important definition is a streamline, and that is the path fluid particles follow. So suppose there's a specific flow, and this red thing is the path that this particle follows, and at a certain instant, its velocity is this arrow. So it has a certain length, a certain absolute value, and a direction. And then what is the definition of the velocity? Well, the definition of the velocity is how the length it travels over the time it travels, and this length then has a direction. So it's ds over dt. And again, we want to talk about velocity in points. So we take the limit to this point. So a very small fluid element sweeping through the very small length it travels over the very small time. Now, a problem with airflow is that we cannot actually see the velocities. So at aerodynamics, we still are very interested, of course, in the velocities at certain points in the flow. And what do we do to make them visual? Of course, we put very small particles inside our wind tunnel or inside the flow, like smoke particles or any other sort of very small grain particles. And you see here examples. This is a smoke traces of flow around an airfoil. So an airfoil in our wind tunnel. At certain locations here in the flow, we let loose smoke. And then you can actually see the velocity directions or the streamlines of your flow. And you can see quite some interesting things. You see that here, very far away, the flow doesn't feels it's not going really straight. It already feels the presence of the airfoil. Very close, of course, there's a strong influence of the airfoil on the flow. So you see that the flow follows the airfoil, but here something interesting happens, right? Something blurred actually happens. And you can see that instead of sort of nicely smooth smoke pattern, you get this blurred smoke pattern. And that is due to small vortices. We will get later, so I will teach you about viscous flows and about turbulence flows. So you get transition to turbulence, and you can get even separated flows. And all kinds of vortices happen, and you can actually visualize them in the wind tunnel like this. This is smoke. You can also do water experiments. We have water tunnel at the mechanical engineering. It's sometimes easier to measure things in water, but then again, how do you visualize it? Here we visualize it with aluminum particles inside the water. And what you can see here, that the flow is actually, here it was mainly attached over a large part of the airfoil of the wing. Here we have almost leading edge separation. So you see the flow doesn't really follow the object, but separates. You get here large blobs, sort of dead air region, large vortices. And this has a detrimental effect on your lift. So it's crucial to know when you have stall characteristics. So visualization, velocity. Now some more definitions. So we have a definition of here is stagnation point. So we had, as you saw, the flow coming over the wing, the streaks of the smoke from the previous picture. You get streamlines like this. At a certain point in time, the particles here, later there, we have here a stagnation point, and that is defined as the point sort of where the dividing streamline hits. All the flow above this dividing streamline goes on top. All the flow below goes below. So that's a stagnation point. And then actually there are sort of only two ways that the flow lets itself felt on the wing. So what does the wing notice from the flow? It's actually pressures and tangential forces. So the forces from the flow, we look at in sort of two directions. I told you about the pressure. So pressure was the force per unit area normal to the surface. So that's here. And the length of the arrow in this case shows you the absolute value of the pressure. So here we have pressures. And the other, of course, force is then a normal direction. So we have normal direction is tangential. So along the surface. And that's called shear stress or friction force. And any flow, even air, has this, because really at the surface, the velocity is zero. So outside, so further away from your wing, you have quite a high velocity, and then through the boundary, inside the boundary layer, the velocity decreases to zero. And this gives a friction force on your object. And more on this in viscous flow chapter. So two aerodynamic forces, pressure forces and tangential forces. Which one is the most important in general for lift? Pressure, yes. Because we're looking for lift, of course, for upward force, and this one has typically, of course, if we have a very high angle of attack, tangential force has a certain contribution, but the largest contribution in the direction of the lift is due to the pressure. And is this, does this airfoil have a positive lift, you think? Yes. How do you see? How do you find, you integrate pressures, right? Yes. So you think about how much force you have pushing it down, how much force you have pushing it up. So you integrate the pressure over your airfoil, and you find that the net contribution of all these airfoils, of all these arrows of the pressures is up. Okay. Now, for you to practice, this will only take you 5 minutes, but please practice with this equation of state. It has to be standard, because we're making it more difficult sort of every lecture. So once you're sort of automatic on this, you never have to look at it again. So I advise you to do some small homework exams. Problems F. Anderson. I'm not sure it's still the page number, because it might have been this previous edition. So it is on page 107, sorry. So instead of 102, if you have the latest edition, it's 107. In the 7th edition. Any questions about this part? No? Okay. Then we continue. So first introduction, the basic quantities, pressure, density, temperature, and the velocities. So far we only have a relation between the scalar quantities, the equation of state. So what we're looking now for is a relation that includes the velocities as well. And where do these come from, the relations? Actually, very basic physical principles. What you will learn in this class is very basic balances, physical balances, typically in one dimension, that we'll let loose. However, the concepts that we use, conservation of mass is not destroyed or created, conservation of momentum, conservation of energy, they also are valid for more complex problems. The really complex flow problems you cannot really solve by pen and paper. We approximate the solution. We cannot even accurately solve the equations that describe this for general flows. But what we do in this class is make simplifying assumptions that make sense for aircraft problems. And using these simplified assumptions, you can, with very basic forms of these relations, still solve problems. And the basic forms are conservation laws, mass, momentum, and energy. The real equations that describe flows in general are called the Navier-Stokes equations, and this is a system of partial differential equations. So it is, we didn't teach you differential equations yet, we didn't teach you partial differential equations yet, so I won't bother you with them. But this system of partial differential equations with velocity components, pressures and densities, we cannot solve. We don't even know for sure that we have a unique answer. You can still earn $1 million if you can prove that there is a unique answer to this system of equations. So what we do is we approximate the solution. And if I have time at the end of the second lecture, I can show you, because that is actually my field of research, I show you how this goes about and what you can actually do with it. But for this class, simple assumptions, simplifying assumptions such we can solve them. So conservation of mass and momentum today, then the energy, which is more relevant for the high-speed flows, I will teach you the next lecture. And the conservation of mass, that equation is called continuity equation, the conservation of momentum, the momentum equation, and we have a very simple form of the conservation of momentum for incompressible flows. I will tell you what incompressible flows are, and this is called Bernoulli. So, first, the conservation of mass. I will clean the blackboards. So this is a stream tube, we call that. It can be a real tube, but it can also be a stream tube in your flow with streamlines. So if we have this is a streamline, and this is a streamline, and along we have streamlines, then flow that goes through this doesn't go out or in at the sides, right? Because the streamlines are the direction of the flow, so nothing will go through the sort of walls. So just think of this as a tube. And we have an inlet and an outlet. And we have a specific amount of time. Well, what happens to this tube if we have a steady situation? Actually nothing. So the total mass of this tube remains the same, right? So what flows in a certain time amount has to flow out. Mass is not created or destroyed. So if the mass is the same, what flows in has to flow out in a certain amount of time. And that is the continuity equation. And it says the time rate of change of the mass of this whole thing is 0. So mass flow in is mass flow out. Now, can we make something a bit more workable from this? Let's first look at what flows in at 1. So what is the mass? Suppose we have a small time period, dt. What is the mass that flows in at this location? I have a certain speed, v1, an area, a1, density of the gas here, rho1. What is the mass of air, suppose it's air, that flows in this period dt? Velocity times area times density. Let's try. Mass, velocity times area times density. So we have meters per second, meters to the third, kilograms, meters to the third. So we have kilograms, meters per second. Is that correct? Area is meters squared. Sorry, yeah. Okay, kilograms per second. Sorry. Indeed, so that is the mass flow, right? So how much mass flows in per second? So this is actually flow of mass. This is the m dot. Because what is the mass that flows in per second? We have to then multiply by dt, right? Yeah? So suppose, I'll draw it. Bless you. What flows in a certain time of t? A certain amount dt. At time 0 we have here, then dt further. How much distance does this travel? v1 dt, indeed. Meters per second times meters. So if we think about the mass that flows in, it's actually the mass inside this volume, right? That flows in a time dt. Well, the volume area on this side is A1, and the volume there is v1 dt. So mass is density times volume. So is rho, density, 1, times volume, that's A1 times the length, v1 dt. So rho a v dt. That is the total mass. The mass flow, indeed, dm over dt, is then rho a v. Now what flows in? This total mass, rho1 a1 v1 dt, is of course the same, equal as what flows out at cross-section A2, right? So what flows in this certain period of dt here? flows out here as well. So conservation of mass says rho 1 A1 V1 dt is rho 2 A2 V2 dt. Dt drops out. So rho AV is constant. And what is this rho AV? It's the mass flow, right? It's the kilograms per second. And that is due to a certain flow coming in over a certain time dt. The length traveled is v dt times the area. So conservation of mass, it's rho AV is constant. Density times area times velocity is constant, and this is indeed the mass flow, so flux m. So what flows in, it's written here also, what flows in flows out, so dm dt in is dm dt out. dm dt, the dm, the mass, is density times volume, rho times AV dt. The dt is dt, so the mass flow is equal to rho AV. Rho AV is constant, so whatever cross-section you put it at, rho 1 A1 V1 is rho 2 A2 V2. Now, please note that also your density can change here, right? So for compressible flows, for flows around aircraft like Boeing 747 or so, the flow goes up to 0.8, sort of 80% of the speed of sound. And that's still subsonic, so the speed is lower than the speed of sound, but quite high relative to it. And as a result, we have significant density changes in the flow. So density plays a role here too. And with supersonic flow, it can even change very, very much the density and have a very strong effect on this. However, for incompressible flows, and incompressible flows are flows that actually, incompressible flows don't really exist, they are an assumption. And the assumption is the density doesn't change significantly. When is this assumption valid? When you have liquids, yes. Yes, liquids, oil, water, we don't have much density changes, right? In a gas, you can compress it, and you can get the molecules closer, and you get strong density changes. Liquid and oil, it's much harder. However, with air, you can also have the compressible flow assumption making sense. And when is this? For what type of air flows can you assume incompressible flow? Low speed, indeed. And I don't have the relations yet to show you. I think in the third lecture, I can show you how you can compute that indeed density changes are small for low speed flows. We say up to 5% density changes, we assume the density to be constant, and that's up to about 100 meters per second. So if your flow, your maximum speed in the flow, of course, it should be the maximum, is below 100 meters per second, we assume incompressible flow, we can work with constant density. And then this becomes easy, right? Then this one drops out. And for incompressible flows, we have a direct relationship between area and velocities. So here, compressible versus incompressible flow. Compressible flow where we have fluid elements where density can change from point to point. However, in incompressible flow, we assume these density changes to be negligible. And it's valid for liquids and low-speed airflow below 100 meters per second. Any questions about this? Okay, then we'll practice after the break and continue. Thanks. Two types of flow, compressible flow and incompressible flow. And for incompressible flow, we have then a simple relation, right? So incompressible flow So rho is then constant in the flow. So AV is constant. So area times velocity. So suppose I have a duct like this. Sorry. Huh? Yeah. Velocity. Yeah, it's a bit, so I try, if I have volume, I try to write out vol, specific volume, curly V, but capital V is mainly velocity. So for incompressible flow, we have easy, AV is constant, so you get a very straightforward relation, right? If your area doubles, for example, your speed halves. But please be aware that it is only for incompressible flow, so really low speed subsonic flow for air. Because for highly compressible flow, supersonic flows, you can have that the area increases and the velocity increases as well. Because the fluid expands and the density changes so much that you have, so supersonic flow, if you increase the area, your speed increases. So please, the AV is constant just for incompressible flow. Incorporate the density in general cases, okay? Now we can do an example, simple example again with this. So suppose we have a converging duct. So in this case, the other way around. A converging duct, converging channel. So converging duct is like this, right? Flow in, flow out. Inlet area is A1, 5 meters squared is given. V1 is given, so the entrance velocity is given. And we have, of course, an A2, exit area, and a velocity at the exit. And the question is to compute the area of the duct exit, A2. So which relation can we use? AV is constant. Can we do this? So can we leave out the density, the rho, assume it's constant? Why? Low speed, below 100 meters per second. The fastest speed we have is at the smallest exit here. We don't know it yet, so it makes sense to check it afterwards, but let's assume we have 5 meters per second, so we have 10 meters per second here, so probably we will not reach the 100 meters per second, but worth to check afterwards. Huh? Oh, sorry, we have it already, yes, it's 30. So indeed, the fastest speed is 30 meters per second, so way below 100. So what is the area of the duct exit? AV is constant. A1 V1 is A2 V2. The question was A2. AV constant, A1 V1 is A2 V2, so A2 is A1 V1, so the area was 5 meters squared. The inlet velocity 10 meters per second. V2 30. So we then end up with the area equal to 1.67 meters squared. So where we had here 5 meters squared, we have here 1.67 meters squared. Now check, is this intuitive question? Yes. Question, what should you do when the velocity is faster than 100 meters per second? When the velocity is not known, well, then you cannot say anything about it. You can try to use common sense. So if we're talking about 5 and 10 meters per second and you don't see a reason why it would speed up, you can assume, but say you assume incompressible flow and because you assume low speed. Quite often in exam questions, we let you compute or we give a maximum point with a maximum speed. So then you can say, okay, that point on the wing is close to the maximum speed of the flow. That is below 100 meters per second, so I'm safe. That is what you in general do. In sort of general applications, of course, cycling, cars, gliders are really low speed subsonic. Takeoff and landing might be a bit parts, of course, low speed subsonic, but cruise flights of commercial aircraft is really not low speed subsonic. Subsonic, transonic, but not low speed. So also from the application, if I say you in sort of what application it is, you can already get a hunch. Okay, that might be worth to check because you sometimes make mistakes. Okay, the area decreases and indeed the speed increases. So for low speed subsonic that makes sense. Well, one important example where we really use this conservation of mass is in our design of our wind tunnels. So this is the latest wind tunnel. We built this 2 years ago. It's called the Open Jet Test Facility. And we use it for a flow investigation, especially around, for example, large objects. Wind turbines, for example. If you have a closed test section and a large object inside, you get a very strong influence of the walls. So this is a wind tunnel without the closed section, so a large open section. It's actually built here on the other side of the street, and air blows out here in a large hole. I think it is, well, it might be a bit smaller than this, but the cross-section of the area is comparable to the lecture room. And this is the test section. So here we put up the wind turbine or wing or whatever you want to test. Now, how does this wind tunnel work? We have here a large fan which speeds up the flow, going through certain veins here because we like the flow to be as low turbulence as possible. So we like to damp out all the small scale perturbations in the flow. And we do that with veins leading it here around the corner and with a screen, anti-turbulence screen, where it goes through certain screens to damp the small scale perturbations. Then the flow is blown over the object here, and we measure their pressures, for example, forces, but we can also do particle image velocimetry, have smoke here or particles, and using laser light, illuminate it, take pictures, and then the whole story for my colleagues starts because you have then pictures with particles at certain time instance, and you have to then correlate them, and that's quite a mathematical exercise. Like I'm solving the equations for flow directly on my computer. He's solving these relations for the particles. Yes. Can we go visit it? Yes, you actually will have a practical in the project inside here. So inside the Open Jet Test Facility, you will have a practical on aerodynamics, measuring forces. Yes. And you can always come in, but you have to with your campus card, you have to activate it for the aerodynamics laboratory. Then you can always come in and have a look while they're doing tests. The Nuna car we also put in there. And then the flow, of course, is sent around again, and here speed up again. So that's the Open Jet Facility. We have a large range of wind tunnels. This is for low speed research. This can go up to 35 meters per second. We also have hypersonic test facilities where we can go up to 11 times the speed of sound, but that's much smaller. Okay. So conservation of mass. Now we go to the next chapter, conservation of momentum. And please bear with me. We start deriving the conservation of momentum from the first law of Newton. F is m times a. So force is mass times acceleration. Should remember this from high school. Oops, sorry. So force is mass times acceleration. Now we're going to apply this to elements in our flow. Elements, and it's this element. I look at it while it's performing flowing horizontally, so along a horizontal streamline. It's flowing in horizontal direction. Now I'm looking at the mass of this element. I will look at the acceleration of this element and look at the force. and see if I can rewrite them in certain properties of the flow, hopefully pressure, maybe density, velocity, to find a relationship between those. So between the scalar quantities I can compute with my equation of state and the velocities. That's what I'm working towards. Now what forces are there? So let's start with the left-hand side. What forces are there on this element? It's flowing. Pressure force, indeed. Because if the pressure here is not, the pressure here is not lower than the pressure there, it would not flow, right? If we have the same pressure left and right, we don't have flow. So we have a pressure difference over this element to make it flow. That's indeed the most important, and that's the only one we will incorporate. Are there any other forces? If you imagine this flow being just somewhere in a room, what other forces are there? Gravity, yes. Gravity, of course. What we'll do is say, okay, it's flowing horizontally, and we will not assume gravity having a major influence. And this is really true for the type of flows we're interested in, around aircraft or so. If you have a bucket of water and you make a hole in it, of course gravity is the driving force of your bucket of water of emptying. But in our type of flows, pressure is the main driving force. So we will neglect gravity forces. Any other forces we might need to neglect? Tau W, frictional forces. Perfect. In a real flow, of course, we have friction. So if we have flow over an object, and the flow attaches to the object, and we have fast flow on top, due to frictional forces, it's only friction that can make this change of speed in the flow. However, this friction is, for our applications, high speed over wings, is only relevant inside the boundary layer. And that's a very thin layer typically. I will show you later how you can compute how thick it is. Thin layer, and throughout this layer the pressure is constant. So the pressure doesn't change much. So I indeed neglect friction. So let's start and think about the pressure forces. So we have pressure forces on this element. Now, the pressure then on this side needs to be different from this one, and then exactly lower to make it flow in that direction. Now, this element is small and it has the following dimensions, dx, dy, dz. So the volume of the element is dx times dy, dz. Then the pressure on this side I call P, and then the pressure on this side is P plus dP. A small change, it's a very small volume, a very small difference. Then I take pressure forces in that direction positive. So this one is P, and that one is minus P plus dP. So let's look at the left-hand side of FSM times A, so forces. Now indeed we have pressure forces, friction and gravity. We neglect gravity, small. We neglect viscosity, friction forces, so we only look at this pressure force. Now, the force in x direction, so the total force, we have here a force, a pressure on this area. And pressure was force per unit area, right? So if we multiply pressure by area, we get the force. So we have the force in that direction, P times the area of this side, and that is dy by dz. So P dy dz is pushing the element in that direction. Then, on this side, we have a slightly different P, namely P plus dP, or we can write dP as dP over dx by dx. That's easier for later, but you can, of course, eliminate these dx's. So on this side, we have P plus dP, but in the opposite direction. And I call this a negative direction, so minus. So the total force is the pressure on this, force on this side, minus the force on this side. Well, the force on this side is then P plus dP, that's this one, times the area. Same area, dy dz. Yeah? So, P dy dz minus P plus dP over dx, dx dy dz. So, P dy dz minus P times dy dz, so that one drops out. So we only left with this one. So the force, net force on the fluid element is equal to this, minus dP dy dz, or minus dP over dx, dx dy dz. So we have the force. Pressure force driving this element to flow. Now we're looking at m times a. So F is m times a, force is mass times acceleration. Now we'll look at mass and acceleration. The first thing is the mass of this very small volume. Well, we have done it before. Mass is equal to density times volume, right? So density rho and the volume of this small object, dx, dy, dz. So there it is. The mass is rho dx, dy, dz. Now the acceleration, a, is the dv dt. So how much the speed changes over time. What I will do now is a bit of trick, rewrite it such that certain bits can drop out later and that we get the speed actually in it. So this looks a bit strange, but at the end we have something that we can work with. So a, of course, acceleration, so dv over dt. I can also write the dx in there, right? I can divide by dx and multiply by dx. So that's what I do. And then I recognize that again I have a v here. So I can write my acceleration as dv over dt, but also as dv over dx times v. Now, I'm going to substitute it now into my relation. Force is mass times acceleration. Force, easy, pressure force minus dp over dx times dx dy dz, right? Then mass, rho dx dy dz. And acceleration, dv over dx times v. Now what do we do here? We can scratch out dx dy dz on each side. On each side we divide by dx, so we can take that out. So what we're left with is this relation. dp, and we have here a minus, we can take that to that side, is equal to minus rho v dv. And this v is velocity. So now we have a relation between pressure, density, and velocity. Very nice. What does it say? Good question, right? Small pressure changes are equal to the density times the speed times velocity changes. So pressure changes is related to density and velocity changes. Can I now just integrate and do something in general or not? Yes? If we try hard enough, yes. It's a bit complicated because this is all small. So what you have these differentials, these d's. So to get a normal relationship, you typically integrate. On the left side, on the left side is not difficult. You have the pressure, just pressure. So that's easy. But on the right-hand side, we have rho's and v's. So indeed, it's a bit hard. So we make our life easy and we first derive a relationship for... Any ideas? For? Yeah, but how can we make life simpler? So integrate this, pressures, and can we assume one constant maybe, not changing on the right hand side? Density constant, thanks. Density constant, for incompressible flows, this is not hard, right? We have just dp and vdv. So we'll now do the derivation. So this is still valid. The differential form is valid for compressible and incompressible flows. We will now integrate it for incompressible flows. So please remember, and also you should be able to derive this. So we might ask you at the exam, please derive Bernoulli equation, because it's important to be aware of what you neglect, gravity, friction. It's not too tough. And then you see where actually your relation comes from. And the first step leads to this equation we just derived, and it's called the Euler equation. Mr. Euler came up with it, and it's quite a useful relation. dp is minus rho v dv. Yes, question. Sorry? Why do we assume that we actually have a pressure? Well, yeah, because we have the idea that the pressure is driving the flow. But you can have it's the same pressure, and you will see here that if you have the same pressure, so dp is equal to 0, what will happen then if this is 0? Velocity will not change. Your dv is 0. So you can have pressure here the same, no velocity. So that's the situation in this room actually, right? But if you get flow, airflow is driven by pressure gradients. Changes in pressure. Okay. So, gravity neglected, viscosity neglected. Oh yeah, what we also did is we assumed steady flow, so nothing changes. Yes, question? No, yeah. Shoot, I got the question. Question is, why is it called moment or conservation of moment equation? We didn't use a moment whatsoever. Well, forces are a part of a moment, but I agree. The true relationship that is behind this, so the partial differential equation is conservation of momentum. And if you simplify that, you get this. So it is related to momentum, but we in the derivation didn't use any momentum, just the forces. Yeah. So. True. We use the momentum in the way that the forces are changing. So the momentum changes. We are incorporating. True. But not very. We didn't define a momentum. And later in the Navier-Stokes equation, you actually define the momentum of a fluid element and look at the conservation of that. But it's quite. I mean, it's very related. Yes. So. Okay, now getting to something non-differential, we're going to integrate this differential equation and make our life easy. We assume density constant. So, constant density, then what we do, we integrate this along a streamline. So a streamline from point 1 to point 2, integrate our relation. dp is minus rho v dv, or dp plus rho v dv is equal to 0. And we integrate it from state 1 to state 2. And in that way, we hope to get the relation between pressures and velocities in point 1 to pressure and velocities in point 2, okay? Now, integrate dp rho v dv. Did I have it written out? No. Sorry. So then we need the primitive value, right? So we have from state 1 to state 2 dp plus state 1 to state 2 rho v dv. We assume this one constant. So what is the primitive value of dp? P, yes, between p1 and p2. Plus, what is the primitive value of rho v dv? Rho v squared divided by 2, right? Because rho is constant, so we can take that out. V squared over 2, if we take the derivative of that, we have 2v over 2, so we get v dv. Between state 1 and state 2. So that is pressure in point 2 minus pressure in point 1 plus rho v2 squared divided by 2 minus rho v1 squared divided by 2. Is equal to 0. Now we collect all states 1 on one side and all states 2 on the other side, so we get P2 plus a half rho V2 squared, right? This one. And this one is equal to P1 plus a half rho V1 squared. And that's our nice friend, the Bernoulli equation. So what does this tell us? P plus a half rho V squared is constant, right? I can write it in state 2, state 1. It's constant along a streamline. I'm integrating along a streamline. So if the pressure goes up, the velocity goes down. And if the pressure goes down, the velocity goes up, right? And the total sum is constant. Now we have a name for this constant, and it's called the total pressure. Because please be aware, what is the dimension of this equation? Well, we have here pressure, newtons per meter squared, plus we add something. So the dimension of this is also newtons per meter squared. This is a pressure. And this is a pressure related to the flow. We call this a dynamic pressure We call this the static pressure. And the total sum of these pressures we call the total pressure or stagnation pressure. And how do you find this? If I'm interested in figuring out the total pressure of a certain flow, what is it equal to? Pressure in a stagnation point. Yes, because if you have V is equal to 0, this term drops out, and you have the static pressure in a stagnation point, or in a very large reservoir, for example, where the velocity is almost 0, that is the total pressure of your flow. Can it change? Not for incompressible flows. For compressible flows, you can have changes of total pressures. For incompressible flows, not, because that's what is staying here, right? Total pressure, always the same, and it's equal to P plus a half rho V squared. Please be aware we neglected gravity, friction, and this is only true for steady flows. And this is the equation, what do you call it? Found by Daniel Bernoulli, Swiss yes, he's a Swiss mathematician, but lived in the Netherlands for a short while. And that's his book. Now this is also an effect of the Bernoulli equation. So quite... sorry. If you apply Bernoulli's principle to flow over an airfoil, sorry for this, but we see here an airfoil. This is a pressure, yeah, I see. I see an airfoil. And on my screen it was yellow, sorry for that. Then this is minus Cp, so minus, we made it non-dimensional, but minus the pressure on the top of the airfoil. 0, going down because it's larger in the minus sign, and then the pressure goes up. So what you see if you go along the chord on the top, you see the pressure goes down, flow speeds up, right? Pressure goes down and then goes up again. So you see here the suction peak here at close to the leading edge, which contributes quite a lot to the lift, but more on that in chapter 5. Well, where we came from, right? Now let's practice. Heb ik nog een bord? Nee. So this is example 4.4 from Anderson. And the question is as follows. So we continue with the convergent duct. We just did the simple converging duct. But now there's more given. Inlet pressure, inlet temperature, and the question is exit pressure. So that was this converging duct, right? With a certain A1, V1, A2, V2. But now we also have P1, T1, and the question is P2. So what relation can we use? Now it's sort of trivial. Later you will get more choices of relations. Relation to find the pressure. Any ideas? Sorry? Bernoulli's law. Bernoulli's law, perfect. Very hard. But you should ask yourself, is Bernoulli's law valid? So can we apply it? Do we have low speed subsonic flow? Does anyone remember the maximum speed we had? 30 meters per second. Thanks. So yes, we can, right? Okay, Bernoulli's law. So P1 plus a half rho V1 squared is P2 plus a half rho V2 squared. And the one we're looking for is P2. So P2 is equal to P1 plus a half rho V1 squared minus V2 squared. Now we had V1, 10 meters per second. We had V2, 30 meters per second. We have pressure at 1, the inlet, 1.2, 10 to the power 5. We don't have the density yet. How do we do the compute the density? What is the relation we can use for the density? Rho is PRT, equation of state. P is rho RT, so rho is P over RT. Now, we assume the density is constant, right, here Bernoulli. Low speed flow. Rho constant. So we can compute the density anywhere in the flow. But where does it make most sense? Where do we have the most information to do this? At the inlet. Yes, we have pressure, we have temperature, so we're there. So we do it at the inlet, at 1. So that's equal to 1.2, the pressure at the inlet. R is still 287. And the temperature is 330 Kelvin. So then we find the density. 1.27 kilograms per meters to the third. Now we're there, we just have to substitute it into the Bernoulli equation. So P2 is equal to P1, so that is 1.2 10 to the power 5, plus a half rho, 1.27, times V1 squared, minus V2 squared. Now please note what is happening here. So the pressure at the exit is the pressure in the inlet plus something, and we have here 10 squared minus 30 squared, right? So this is a negative number. So we subtract something from the inlet pressure. So the outlet pressure is lower than the inlet pressure. Does that make sense? Yes, indeed, because it's going faster, right? 30 meters per second, 10 meters per second, incompressible flow, Bernoulli, so indeed. So that's always a check you can do to make sure if you didn't make a mistake. And if you compute it, you find indeed that the exit pressure is slightly lower than the inlet pressure, 1.195, 10 to the power 5. Please note also, it's not a major dramatic pressure change, right? From 1.2 to 1.195. And that is also representative for incompressible flows, for low speed flows. If you have compressible flows, high speed flows, you get much more dramatic pressure changes and density changes. Questions about this? Wow. I hope you will not be ill tomorrow. Bless you. Okay, one more example before I let you go, and this is instead of a channel a bit more relevant for aircraft applications. Airfoil in a flow of air. So here we have our airfoil. We have upstream conditions, far field conditions, where we didn't know there was an airfoil. And they are given pressure, 1 atmosphere, velocity, 150 kilometers per hour, and density, 1.225 kilograms per meters to the third. Now, at this point, on top of the airfoil, a pressure is given. Now, the question is, what is the velocity in this point? So this airfoil is in an upcoming stream. So you can assume it is a wind tunnel test, for example. Right? Wing in wind tunnel, we blow air over it, air of 150 kilometers per hour, and we get certain flow conditions on top of the airfoil. So how do we go about this? What relationship do we need? Bernoulli, indeed. Velocities and pressures again. So we start with Bernoulli. Well, and then the first question you should ask yourself, Bernoulli, from where to where? Well, that's trivial, right? From infinity to A. So P infinity plus half rho V infinity squared is equal to PA plus half rho VA squared. We're looking for VA. So that one is equal to P infinity minus PA divided by a half rho and plus half rho VA squared. Sorry, V infinity. Ooh. Square roots. So that gives us our VA, right? So we just manipulate this equation, take PA to the other side, so P infinity minus PA, divide by half rho, so this one, divide half rho, so we get this one divided by a half rho. We, oh, this one needs to, sorry. We divide by half rho. So we have the plus half rho V squared over half V rho. So this one becomes simple. So VA is then equal to 2 square root of 2P infinity minus PA over rho plus V infinity squared. Only question is rho. What do we do with this rho? Constant, yes. And we have them, it's given at free stream, right? So we take the rho infinity. So we assume constant. Then it becomes simple. 2 P infinity pressure at point A. What do we do with V infinity? Do I write 150 squared? No? Yes. We have to get it to meters per second. So please be aware, you cannot just put in all kinds of units. We have here kilometers per hour and we need to transform it to meters per second. And then we find, for the velocity in point A, 64.7 meters per second. And now it's a good point to do the check, right? If this was above 100 meters per second, you needed to do something different. But we're okay. Okay, 2 more remarks. One remark. Please practice 2 test problems, 4.3 and 4.4 from Anderson. Also tomorrow there will be the instruction related to this lecture. Nando Timmer, my colleague, will oversee that, but also there you can practice, but please practice this before. And then an important remark about tonight. Does anybody want to eat tonight? No? Oh, okay, then it's irrelevant. Tonight there's a lecture of Wubbo Okkels. It's for the Dutch only? Oh, okay. Oh, sorry. You had it already. Oh, sorry. So no free dinner for you. Sorry. Okay. See you tomorrow. Thanks.
Please visit our OpenCourseware website for more information. See you at our next